Recording is rolling. It is Monday, April 28th. So I gave everybody a stats packet. A stats packet myself right here looks about like this. Like normal, all of us have different numbers, but we have the same scenario. So I'll be going over this with you guys for about 3 days. Now, the reason we're going to do a little bit of statistics is because I think it helps to know some statistics before we go into quantum mechanics, which is the final topic in this class. You have to think a little bit differently, know some stats. It conceptually makes a lot more sense. Right. Guys, show hands. How many guys are in a stats class or have taken stats? Take us out. 1, 2, 3, about 3 guys. All right, pretty good. So, guys, what we do for the next 3 days, because it takes us 3 days to go through this packet, should be a really good review of most of the major concepts that you guys have learned in stats. Of course, not everything, because we're just doing 3 days from a whole year-long class. Right? And because if you've never had stats before, then stats is good for a lot of things. I mean, obviously, quantum mechanics is doing a setup for that. But if you do any hard science, you're publishing any results of any scientific experiment, you're going to want to compare an experimental group to maybe a control group or some kind of placebo group. That's going to involve stats. This is a class that changed the way that I view the entire world. I mean, a lot of classes have, but stats I would definitely put on that list. Right? So know that. All right. Final exam review, because we got final exam coming up. So I did finish your guys' final exam finally over this weekend. And I got the study guide posted to Google Classroom. You guys see right here, study guide? So I do need to run this to the copier. So I'll get you guys this the next few days. In fact, actually, I think probably what I want to do is do a few days of stats, then probably do the final exam review, and then do quantum mechanics just to for sure get it all in there. All right, okay. So anyway, if you want access to it early, that is right there for you guys. All right, so you guys know where to find the study guide, the exam review. All right, so it's there. All right. We got, of course, final exam schedule. Here's the final exam schedule for most students. All right, so juniors and sophomores, we got May 22nd to 28th. There's a senior exam schedule. It's a little bit earlier than that. So senior exams is May 12th through 16th. We will have finished the final exam review by the time all those dates roll around. All right, so everybody good with the agenda, what we're doing? Right. All right, so let's take a look at the stats right here. Stats. So put your name on your paper. Everybody got their name? All right. Period 5. You guys are period 5 in front of me right now. Good. Okay. Now, there's a couple of formulas here. One refers to mean average, which I think you guys have known how to take a mean before you ever walked in this class, right? You just add up the number, and then divide by the number in the set, right? So we're going to do that. But there's also this maybe more abstract concept called standard deviation, which is like how spread out is the data. So we're going to do lots of examples of that today. And then on the right side of the page, about halfway down, there's a third formula. And well, it's going to take a while to build up to that concept, but you guys will see that before you walk out of class today too. All right, so we're look at it here. So big picture. Do you guys see number 1, number 2, number 3? I got heights of 5 dogs, heights of 5 humans, and heights of 5 house cats. You guys see that? Right. Oh, also, I did amend this from last year. I came up with a better example. Oops, I forgot this. You guys see where it says tree 1, tree 2? Yeah, scratch out tree and write cat. Cat. Cats. 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 Kitty cat. Got 5 cats going on there. So I need to go back and fix that, right? Because those would be a better example anyway, right? Because if you're comparing heights of things, right? There are obviously different average heights. Even before we run the numbers, because I gave everybody different example numbers that are kind of reasonable. Okay? Guys, out of these 3 populations, who do you think is tallest on average? Humans, dogs, or cats? Probably humans, right? And so, of course, we'll confirm that later, but when we get numbers in these boxes and then run them later, right? I think humans are going to have probably the tallest average height. Right? But what about this concept? Because if you look at all humans, is there some variability? We have short people and tall people? Yeah, right, but we're all kind of somewhere between like 5 and 6 feet, somewhere in there. We're going to be doing centimeters, but what if human heights were scaled kind of like dog heights? What if human heights mirror dog heights? Or had like somebody that was like 2 feet tall and somebody was 8 feet tall? Wouldn't that be more realistic to distribution of dog heights, kind of? Right? So what I'm trying to get at is a different concept, not average height, but how spread out is the data? And the stats term for that is called standard deviation. Right? There's a similar term called variance. Right? Guys, who has more variability in their heights, dogs or people? definitely dogs, right? These little tiny foo-foo dogs, these big old Great Dane dogs. It's all in the middle, right? Now for people, yeah, people are all about 5 or 6 feet tall, but dogs, there's a huge variability, right? What about when we get to cats? Guys, what about the size variability on cats? Is there a huge variability or all house cats about the same size? What do you think? Yeah, I think all house cats are about the same size. If they go home and they're like, oh, I just got a tiger just hanging out in the kitchen. No, cats get too big and you start to look delicious. So how can we represent that with statistics? And of course, I got some data numbers here. There's some bell curves. We're going to map this onto. Right? But big picture here, big picture. I'll show you guys one bell curve now. We'll expand this to these big populations later. Right? What if I did heights of humans? Okay. Now tomorrow you guys will do a lab version of this. I'll give you guys some meter sticks. You guys got to measure each other's heights. Okay. What if I put height on this horizontal axis? I'll put frequency on the vertical axis. Okay. I'll say scale to some increment. I don't know, maybe inch, centimeter, whatever. Okay. And I start pulling like hundreds of people, maybe thousands of people. And I start clocking like here's like the shortest people. There's only like 1 or 2 of them. And then the next increment, let's go a centimeter up. Okay, there's a couple more, not too many more, but a couple more. Okay. How about the next centimeter up? Okay. And then you guys can make it a bar chart. I've seen this also called a histogram. You see, maybe there's something like this. Okay. And then for the taller heights, well, it's going to start to peter off. Now there's only a few people that are super tall. I got one like NBA player right here. Okay. So do you guys see kind of the big idea of where the shape could come from? Okay. So short people, there's only a couple of them. Super tall people, maybe the short people's like, I don't know, like 4'10", and the tall people's like 7'5". Okay. And then most people are kind of in the middle, about 5.5 feet, something like that. Right. Or if you did metric centimeter. Right. But if you stand back and look at this, you guys see an overall shape emerging? That's like a bell curve. You guys see kind of a bell curve looking shape right there? You see that? Right. Now, I'm going to make believe that this is what's called normally distributed. So normal distribution. Now, are heights of people really in real life normally distributed? Probably not exactly, but a lot of data are, and we're just going to run with it for the story. Right? Because I want to look at a couple of properties of this bell curve. Now, right at the top of the bell curve, guys, this top position right here would tell you what property of height of people? Average. Aha. I call this average. Is the average? Right. Now, for a normal distribution, you guys know there's different kinds of averages. There's what 3 types of averages am I thinking about? They all start with M. Mean, median, and mode. Mean, median, mode. Right. Mean, that's this formula right here we're about to apply pretty soon. Right? That's like you add them all up, divide by the number. Right? Median is like the middle value, which has some advantages for some cases, like median income is a good example, right? And mode is like the most frequently seen number, right? Now, in a normal distribution, those are all the same thing. Okay? I'm going to refer to that either as x bar, so an x with a bar over it, or mu. You'll say like that, right? Now, if you're taking a stats class, you guys know one refers to a sample, one refers to a wider population. I'm not going to distinguish the difference in this class. I'm just going to call it all the same thing. So I might use those characters interchangeably, right? You guys okay with that? Mean average, right? Now, remember a few minutes ago, I was asking if you sort of compare humans to dogs to cats, and humans have some variability. Dogs are like way more variable. So if I was looking at dogs, you think it'd be way more spread out, right? And cats are all kind of the same size. Well, hopefully, you're a house cat, right? So wouldn't that be like a really skinny bell curve? Something like that? Right? And how could you measure sort of how spread out is the data? Well, one way to do it, a really good way to do it, you guys see the middle of this curve is concave down, like an upside down bowl. But you guys see that the tails are like concave up? Like the concavity switches. Do you guys see the point where the concavity switches? Actually, there's 2 points. There's like one there and one there. You see where the concavity switches? Right? Now that point, also that point, has a name. It starts with an I. And if you're in stats or if you're in calculus, I bet you know what that point is called. It's called a what point? That's right. That is an inflection point. Inflection point. or over here, I'll call this I key for inflection point. You see that? Inflection point. Right. Well, you could measure from the mean to the inflection point, and it'd be the same distance on the other side. You see that? Right. I think you guys might be putting this together. Maybe if you're either looking at this packet or maybe anything I've said so far. What am I going to call that distance from the mean to that inflection point? It's called one what? Standard deviation. So I'm going to spell that out. Standard deviation. Okay. And for that, I might use lowercase s. Okay. Or you might see a lowercase sigma, that little curly looking sigma. Right. Again, one refers to a sample, one refers to a larger population. I'm just going to sort of use those interchangeably for next few days. Okay. Just kind of same concept. Right. All right. Is everybody okay so far? All right. All right. So with those concepts in mind, let's look at some actual data values. And I tried to pick some kind of reasonable data values. Right. So how are these numbers going to show up? How's it going to map onto these three bell curves over here? Try it out. Right. So first thing, I got 5 dogs. Looks like we're starting with dogs. Everybody see there are 5 dogs? Right. Now, little side note here. We're going to make believe that these 5 dogs somehow tell us about like thousands or millions of dogs at large. Right. Realistically, if you were an actual statistician or if you want to do this properly, do you think you would realistically have to get approximately 1,000 dogs? Yeah. Now, once you have 1,000 dogs, now you maybe got a clear idea. Right. We're going to really shortcut this. We're going to say 5 dogs tell us something, but let's run with it. So number 1, let's get the mean average. So I'll call it X bar or what else was I using for that again? Mu, if you like. Right. I'll just say equals. Right. Now this is one that, again, I think everybody would know before you ever set foot in this class back in August. Right. So I'm going to add up my 5 dog heights. Here's doggo number 1. Doggo number 2. Number 3. Number 4. And number 5. Okay, these are all centimeters. If I'm attaching my unit, these would all be centimeters, right? Okay. Throw that all in parentheses and then divide by 5 because there's 5 dogs. Okay, did you guys add up your 5 dog heights and then divide by 5? All right, so calculator time. Let's do first dog. So open parenthesis, I meant. Open parenthesis. First dog plus second dog plus third dog plus fourth dog plus fifth dog, then close parenthesis, then divide by 5 for your 5 dogs, and hit enter. Okay. Now, if you did this correctly, the number on your screen should be a number that's kind of in the middle of all the dog heights. Mine is 89.4. No, it's centimeters. So everybody has centimeters. Okay. That's the answer to this first box right here. Okay. And remember, if this is correct, then you should have a couple of dogs that are shorter than that, a couple of dogs maybe taller than that, maybe one's kind of close to that, maybe a little shorter, a little taller. You guys have something about like that, right? Like if you type this all in and you got like 275, then you know that that number is way outside the set, so you punch something wrong into the calculator. Right? Is this working for everybody? It's good. All right. So I think you guys know that. Right. Dog height. Now, how spread out is this data? That's to say, what's the standard deviation? What's this spread from this average value to this inflection point on this bell curve? Okay. Now, for this is going to require a whole process. Do you guys see here it says standard deviation S equals? There's a big old square root. You guys see that? Right. I'm going to walk you guys through this process. We're going to do well, here, just follow along with me here. So let's do S equals. Okay. Now, if I follow this process, I got a square root, I got a summation in here. And do you guys see where it says x sub I minus x bar? Okay. So if I start with that, I'm going to kind of start in the middle of this process and then branch out. Right? I'm taking each individual dog height and subtracting the mean. So my first dog was this tall, centimeters. Well, I'll leave off the unit centimeters, but you guys know these are all centimeters. Okay? And subtract the average, which I just got right here. Right, and you have a little bit different average. You guys got that? Right. Right. Now, okay, so everybody can subtract their shortest dog minus the average. Right. Everybody should have a negative number. Does everybody have a negative number at this point? Okay. Now, suppose let's I'm gonna take a path off the beaten path for a moment. Okay. Suppose you took the differences for all 5 dogs, and then you added up those 5 differences. Every single one of us, you, me, your friends, would all get the same number. What number would you get if you? Let me say that again. So I have a difference here that's negative. What if I did that for all 5 dogs and I added up all those differences? What number would I have to get? Zero. Isn't that true? If you add up all the differences, would it necessarily have to zero out? Okay. So I'm trying to get you guys to think critically about this. Because the next step is I'm going to square those differences. Guys, if you have any difference, negative or positive, and you square it, that makes it always a what kind of number? Positive, right? Positive. Okay. Right. Now I see a sigma, a capital sigma, which means I'm going to add up the squares of the differences for the 5 dogs. Can you guys do that right now? Here, I'll do mine. You guys do yours. So the next dog is this tall. Of course, it's centimeters. Well, it always bothers me to not put the unit. I'll throw them the unit right here. Okay. Minus the average. I'm going to square that difference. Let's bring in the 3rd dog. Minus the average. Ooh, this dog's almost average. So his difference is almost 0 itself. Right? Plus, let's bring in the 4th dog. Difference, square, plus, and then 5th dog. Difference, square. Okay. So at that point of the process, add the summation of, because I've added up 5 different values, right, the squares of the differences between each individual dog and the mean of all the dogs. Okay. Are you guys also at that point? Is that okay? All right. Now there's a couple more steps to this process. The next step is, you guys see after summation, you have to divide by n minus 1. Is that divided by n minus 1? Right. So we take those 5 squares of differences that are all summed up, and we put that all in parentheses, and then divide by. Now, since I have 5 dogs, you have 5 dogs, I'm going to take 5 and then subtract 1, which brings it to 4, right? Is it 5 minus 1, 4? It should be the same problem. Okay. Now, this, I'm not going to quite get into today, but here, I'll label it in pink ink. It's called degrees of freedom. Yeah, so it's just part of the process. If you wanted to Google that term, you could read up more on it. Or if you take a stats class one day, maybe I'll have a stats teacher that goes a little bit more into detail of why you subtract 1. But we're just going to run with it. Okay. But there's one last step. And the last step is to take the square root of that whole thing. I sort of think of that as being kind of undoing the squares that we did before. Think about it that way, maybe. All right. So I'm going to square root this entire process right here. Square root this whole thing. Okay. Throw it in parentheses just for good measure. Like that. And out of this, I'm going to get a number. Right? Now, it's going to take a while to punch into the calculator. What's probably a good idea, because otherwise my calculator runs out of space, is I'm going to reset my calculator. Let me do that. I'm going to hit second 0. Can you guys do that too? Second 0. Actually, go ahead and do that. That's good practice, because last class had a bunch of stuff punched in. Great. You guys hit second 0 and then scroll over to yes for reset. Okay, so I just reset. I just cleared all the memory from my calculator. All right. Now I'm going to type all this in. Actually, I'm going to break this down into different steps. So, do open parenthesis, 1st dog minus average square, well, close parenthesis square, plus open parenthesis, 2nd dog minus average, close square, plus 3rd dog minus average, close square, plus 4th dog minus average, close square, plus 5th dog minus average, close square. Right. All right. So when I hit enter, I'm getting a big positive number. That's not the answer to everything. It's just this numerator part right here in parentheses. Okay. Okay. Are you guys up to about where I am? Then I need to divide by, and then in parentheses 5 minus 1, or you can just say divide by 4 if you want. So it's 5 minus 1 down here. Then hit enter. Right. Now I still have one more step to go. Guys, what is that last step? What's the last step I have to do? Yeah. Take the square root. So I'll hit second square root, second answer, or you could do whatever number you just got to the power of 0.5. That's a different way to also take the square root. Okay. Anyway, get an answer out of this. Yeah, that looks about right. Okay, so I'm getting this number on my calculator screen. Now that number has the unit centimeter attached to it. And since you guys also have centimeters, that's also true on yours. Okay. And remember what that number represents. What does it mean? All right. So what that number means is what's the gap on the bell curve from the mean for all the dogs to this inflection point. That's what that means. Right. Here's a little bit different context. There were about 3 of you guys who said you're taking stats right now. All right, guys, I'm going to ask a question that if you're taking stats, you'll be able to answer this. Okay. If you start from the mean and you go plus or minus 1 standard deviation, isn't that kind of what we're talking about with this number you just calculated? So if I take my average dog height, call it 89 centimeters, I do plus or minus this 19 centimeters. That should cover what percentage of all the dogs? About 68%. 68%. Yeah. 32 on the high side, 32 on the low side. So it'd be 68. Right? You guys see that right there? Right? Yeah, if you're in stats, plus or minus 1 standard deviation should cover 68% in a normal distribution. Plus or minus 2 standard deviations, because you could go up even more standard deviations. That's what percentage is that? Like 95% of your data. If you go plus or minus 3 standard deviations, so like 99.7%, I think, something like that, which is almost everything, but there's a tiny bit on the tails. Right? It could be super tall or super short. Right, everybody good with that concept? Right, so back to the packet then. That's this right here. All right, everybody should have the first 2 boxes written in. Right, does anybody not have the first 2 boxes? Is everybody okay? Everybody keep it up with me? Okay. All right. Now, you guys want to see the easy way to do all this? There's an easy way the whole time. So, in your calculator, again, make sure your calculator is cleared. I'll show you guys again in case you didn't do it before. Hit second 0, scroll over to yes, reset the whole thing. All right. Now, if you're taking stats and you know how to find the mean and standard deviation with a graphing calculator, go ahead. All right. But most of you guys, this is the first time you were doing this. So you also have the small calculator. So does everybody have one of these calculators in your hands? A TI-30X2F. Everybody's got one of these. So hit the same keys that I'm hitting. Hit second stat. Now, above the cosine key, there's a key that says data. And right above that, in white letters, it says stat. Get that? So right above the cosine key, it says data. And then in white letters above that, it says stat. And I can access that by hitting the second key. So I'm going to hit second stat. And on my screen pops up 1 variable. Right. Guys, does anybody's calculator not say 1 variable right now? Everybody says that? So hit enter. Enter. And a word popped up on your screen. You guys see it says stat? Okay. So now it's ready to handle statistical data. Does anybody not say stat on their screen? So everybody's calculator says stat. Now, you guys remember that key that says data right above the cosine? Hit that key that says data. And X1 should pop up on your screen. Okay. Because right now, who does not have X1 on their screen? So everybody has X1 on their screen. Right? All right. And now here's where we're ready to type in some individual dog heights. Well, we'll do it for dogs, and then for people and cats, we'll do later. So remember my first dog was this many centimeters tall? Guys, go ahead and type in your first dog height. Everybody just type in their first dog height. All right, everybody good? Okay. Now, you guys see the scroll keys right here? Scroll down. It says frequency equals 1. Oh, yeah, there's exactly 1 dog. That's that height. If there was like 20 dogs, then I could type in 20 at that point. But there's only 1 dog. So I'm going to keep scrolling down again. X2. Woo! Ready to type in my second dog. My second dog is this tall. Scroll down. Frequency. Yep, there's only 1 of those dogs. Scroll down again. X3. My third dog is this tall. Scroll down, scroll down. My fourth dog is this tall. Scroll down, scroll down. My fifth dog is this tall. Now I just typed in the heights of all 5 dogs. Okay. Oh, how are you guys doing? Do you guys also have your 5 dogs typed in? Right. You guys ready to have the calculator crunch all this data for you? So to the right of data, it says StatVar. It's right above the tangent key. It says StatVar. You guys see StatVar? So hit the StatVar key. And the calculator will do all that process for you. So n equals 5. Yep, there's 5 dogs. Everybody should say n equals 5. Scroll to the right. X bar, well, that would be the average. Hey, guys, is this number matching this number right here? Right? It should. It should. This number should match this number. And then scroll to the right again. Now, this is S for standard deviation. this number should match this number. You guys remember we just did this whole process with this crazy looking square root and got a number out of that? And it looks like the calculator knows how to do that too. Take care of it for you. Everybody get that? Is anybody's numbers not matching? Oh, good. It's all working. All right. Now, that's all I'm going to care about for this class for the next few days. Here, a little side note. You guys see to the right of that says sigma? That's a different kind of standard deviation called population standard deviation. I don't care about that one. So we just care about the sample. Okay. So we're only ever going to use that in this class, which is, again, just for the next 3 days. All right. Everybody good? We're good? All right. Oh, let's do 5 humans. Now, 2 ways you can handle 5 humans. You can just overwrite each data point one by one, or you could reset your calculator and it'll for sure clear everything out. But then you need to reset it. So let's go second stat again. 1 variable, yes. Data. Okay, now I'm ready to punch in these 5 humans. Here's my first human, height. Scroll down, scroll down. Second human, scroll, scroll. Third human, scroll, scroll. Fourth human, scroll, scroll. Fifth human. Okay, now I have my 5 people typed into the calculator. How about you guys? You guys all right? You guys got your 5 people? All right. Then hit stat var. So n equals 5. Yep, I definitely have 5 people typed in. X bar, your average. So here's my average human height. There's my average right there. Okay, you guys also find your average? Okay. Scroll to the right one more time. Standard deviation. So again, this is like a plus or minus factor. It's some number of centimeters, but I gave you the unit on the paper already. So it's like that. Okay. See if you guys have been following what I've been saying for the last few minutes. So if I go with my numbers, suppose my numbers are representative of like all like billions of people and normal distribution. Okay. If I have an average height of 175 centimeters, plus or minus the 7.28 centimeters, if I start from an average of 175 and I branch out plus or minus 7.28, what percentage of all people would that represent? 68%. That's right, 68%. You got, of course, some that's way taller than that, some that's way shorter than that, but about 2/3 of all people should be your average plus or minus 1 standard deviation. All right, you guys good? All right, you guys ready for 5 cats? Cat time. Go to data, or you can clear it out, whatever. I'm just going to override the data there. Here's my first cat. Scroll, scroll. Second cat. Scroll, scroll. Third cat. Scroll, scroll. Fourth cat. Scroll, scroll. Fifth cat. Okay, I just typed in my 5 cats. Did you guys type in your 5 cats? Okay. Then go to stat var. N equals 5. Yep, there's definitely 5 cats. Scroll to the right. Average cat height is this many centimeters. Right. If you did it right, then of course your average should be a number that's kind of in the middle of those 5. Yeah, looks about right. About right. Kind of in the middle. Okay. And then scroll to the right one more time, and you get your standard deviation. Yeah, this is like your plus or minus factor. All right. So what I could say then is if my cats represent a population of cats, the average cat height is going to be 24 centimeters tall, plus or minus about 1.5 centimeters, should cover about 2/3 of all cats. Feel a little taller, feel a little shorter. All right, is everybody good? Numbers looking about reasonable? All right. Now, if you've been putting this in the calculator correctly, and if you did number 1 on paper correctly, then of course you should be getting a match so far. Okay. There's 6 more questions on the front page. So if you're getting the multiple choice answers when we get to these 6 questions, then you'll know you've done everything right. But I think you're good. All right. But before we get to that, we got to handle these bell curves. So, now I've got 3 bell curves. Now, on paper, of course, I did 1 bell curve with you guys just to get the concept. Okay. But now we're comparing these 3 populations. I have dogs, humans, and cats. Well, which curve is which? Let's start with the curve on the right. Okay. Actually, while you guys are thinking about it, let me give you guys some hints. Okay. If you go further to the right, that indicates, guys, what would make a curve go further to the right? If it has a higher average height. Yeah, higher average height pushes it further to the right. Yeah, guys, could I do this? Could I break this into like a bunch of bars, like a histogram? Suppose I was pulling not 5 people, but like hundreds of people. And I said, like, what's your height? What's your height? What's your height? And to the nearest centimeter. And then I stack them all up. Could I make a bar chart about like that? Right. And I can do the same thing for cats and for dogs. Right. Let's look at bar chart for tall, skinny one here. Oh, yeah, go ahead. Yeah. All right. So Bill's got it figured out. Right. So how about you guys? Right. So this curve on the right, you said had to be what again? Humans. Here's humans or people. Right there. Right. And you know that from two features. The fact that this bell curve is shifted all the way to the right corresponds to the largest average height. Do you guys see these three boxes right here? 1, 2, 3. Isn't the tallest height also humans? People are taller than dogs, also taller than cats, right? But there's another feature of this graph. Guys, look how spread out each one of these curves is. Oh, guys, which one's the most spread out? Yeah, dogs, which would have to be the middle one, wouldn't it? Dogs. And which one is the least spread out? Cats, which would have to be this one here. And humans are kind of in the middle. We don't have nearly as much variability in our heights as dogs do. We have more variability than cats. Cats are all about the same size. Is that true? Okay. Right. So for all those reasons, right? Here's another detail, one more detail I want to point out. You see the areas under those three curves are all about the same area. Like if you made this out of Play-Doh, it'd be like the same quantity of Play-Doh to make each other, or same amount of paint to paint them all. Right? And what that represents is that each curve represents 100% of its own respective population. Right? Which means that, like in the case of cats, if it's a really skinny curve, consequently, it's going to make it look like it's really tall. So it's like a tall, skinny curve. And dogs would be the opposite. They're so spread out that like the percentage that are like the average is going to be a relatively smaller percentage for that particular population. Right? Is that clear? Right. Then further to the right is taller average value. Right? And humans are the tallest and the cats are the shortest. All right. So is everybody okay with those three bell curves? All right. So I have a new concept for you guys and then 6 follow-up questions. And that'll take us to the end of today. So the last concept for today, I got a new formula here. It's called Z-score. Oh, it says exactly what it is right here. It says Z-score represents the number of standard deviations from the mean for a particular, I'll call it a particular individual. And it's calculated with that above formula right there. To determine the Z-score for, well, we're going to find 6 Z-scores and then say, what does that Z-score mean, right? So here, I'll spell this out here. So Z-score equals, I'm going to change the notation a little bit. So I'll take an individual. I'm going to subtract the average. Now here I put mu for average, but I'm going to change that to X bar. And then, yeah, if I stop right there, wouldn't that tell me right away, is the individual taller or shorter than the average? Isn't that what that means? Right. But I don't just want to know taller or shorter. I want to know in the context of an entire population, how much taller or shorter? Are you really, really, really tall? Are you just a little bit taller than average? Or same thing for short, right? And the way I can do that is I can get a count of the number of standard deviations. The way to do that is take this difference and divide by standard deviation, which I'm going to call S. And on the packet, I typed a sigma, but I'll call it S. Again, I'm using those interchangeably so much, right? So remember what this is. So Z-score tells how many standard deviations from the mean for a particular individual. Okay. Okay. So you're taller than or shorter than average, and how much so? Okay. And there's still there's still a little bit more I have to say on that. But let's do a little bit of number crunching, and then then I got a little more. All right. So number 4 and number 7 both refer to the dog. So let's do number 4. A dog of height 68 centimeters. So let's get a Z-score on this dog. Now my dog on number 4 is 68 centimeters tall. Okay. Now right away I know this dog is shorter than average because my average dog is 89. 4 centimeters. All right. But how much shorter? Is this dog a crazy, crazy short dog? Is it just a little shorter than average? Well, I can know by taking that difference and dividing by the standard deviation, my like plus or minus factor, which is also centimeters. Centimeters over centimeters. I'm going to get a number out of this. All right, are you guys also following along with your own packet? So see what we got here. Take this individual dog, subtract the average of all dogs, and divide by the standard deviation of all dogs. Oops. All right, I'm getting Okay, I'm getting this number right here. Right. Which if you've been doing everything correctly so far today, you should be getting a multiple choice answer that rounds to that. It might round a little bit. Right? All right. You guys getting a multiple choice answer on that? If you are, then you're on a good track. All right. Is that okay? So what that means is this dog is shorter than 1 standard deviation. Follow me. All right. Guys, watch this. Guys, pick up the whole packet. Flip the whole packet over. And on the back, you see a couple of bell curves and a table. Now, tables are two halves. There's a less than average table and there's a greater than average table. And if you look at the diagram with the bell curve, you see we're shading the bell curve up to some particular value, right? Now, this bell curve in this table is geared for any normal distribution. Do you guys notice that the z-score you just calculated is a unitless value? As centimeters compared to centimeters, that's unitless. Well, I could swap any particular metric. I could do like what's your blood pressure or what's your your body temperature, right? I could have any data that I'm taking, and it could all normalize to this particular bell curve in this particular table. Right? It's all normalized. Right? So what does it mean to have a z-score of negative 1.12? Well, I can see it here. Now, negative z-scores are on the left side, so I'm looking at the left side of the table. Okay. You guys see this go from negative 3.5 to 0, and then the right side goes from 0 to 3.5. Okay. So this z, that's the left column. You guys see the left column is marked z? Right? That's what I've been looking at. Right? That is the number of standard deviations from the mean. So what is it for negative 1.12? So here's negative 1.1. And then going across, I get more granular. Guess you're going across the top of the column, 0.01, 0.02, 0.03. Get that? So let's go to 0.02 right here. This right here, this cell says 0.13. Guys, 0.13. Is that like 13%? Is that what that means? Right. What that means is that this particular dog is so short that he's only taller than 13% of other dogs, which means that he's shorter than the other 87%. That's what it means to have a z-score of negative 1.12. You guys got that? All right. Let's try another dog. Let's do number 7. You guys ready for number 7? We're going to find the z-score on the other dog. So just, back to the front here. Just get right to the right. Got a different dog, different height. How about this many centimeter tall dog? So put this in parentheses. I want to subtract the mean. It's the same mean because I'm comparing the same population, centimeters. Right. Now, right away, guys, the fact that my difference is now positive, I'm going to get a positive z-score. Does that tell me I have a taller than or shorter than average dog? He has to be taller than average. He's greater than me. Right? How much greater? That's what we're trying to answer. So divide by the standard deviation for the population. Let's see what it is right here. So open parenthesis, take my first dog, subtract the mean of the dogs, put that close parenthesis, divide by the standard deviation. Right? I'm getting this number right here. A z-score of less than 1. Okay, so guys, if it's a z-score less than 1, but it's positive, that means, yeah, you're taller than average, but not crazy significantly taller than average. Oh, and I'm getting a multiple choice answer. Are you guys also getting a multiple choice answer on both 4 and 7? Is it? All right. I'm curious. Let's say on the spell curve on the back. So what's 0.77? So here's a z-score of 0.7. And then go to the right, 0, 1, 2, 3, 4, 5, 6, 7. It's right here. Now this I'm going to round this a little bit to 0.78. We'll call it 0.78. You guys see that right there? Right. Which means that this dog, he's taller than average. He's taller than 78% of other dogs. Which means that he's shorter than another 22%. So yeah, taller than average, but not crazy taller. You see that? You see that? All right. You guys ready to do people? Number 5. We got human height. So let's do number 5 right here. Z-score for this human is this tall, this many centimeters. Okay. Well, what does that mean? Is that tall? Is that short? Well, let's subtract the average. Now, here's my average right here. Okay. Now, right away, I'm already seeing I have kind of a shorty right here. All right. But how much short? Well, group that together, divide by the standard deviation. Calls a person fun size. That minus that, put in parentheses, divide by that. All right. Ooh. Yep, that's definitely fun size. I'm getting a pretty big negative score right there. 275. Right. Yeah, so that's a multiple choice answer. Right. What does that mean in context? Negative 275, that's pretty significant. Negative 275. Oh, definitely. This person is so short. 0.003, that's like 0.3%. It's taller than only 0.3% of other people. This person is shorter than 99.7% of all other people. Okay. Number 8. Yeah. Suspect. How about Z-score for, what if the person is 175 centimeters? But wait a minute, my average was 175 centimeters. So I'm doing number 8 right now. Okay. Guys, what is, I don't even have to finish the formula. What is the Z-score for this person on my paper? 0. It has to be 0. It doesn't even matter what the standard deviation is, which happens to be this, but whatever. Okay. Because if you have a z-score of 0, that corresponds to being exactly average. Let me show you guys that's true on this table on the back. This table. So z-score is 0. You guys see right here? 0.00. Here, you guys tell me. What number does that say right there on the table? Right there. It's the top left corner on the table. Huh? 0.5? Guys, 0.5. Does that represent what is a percentage? 50%? 50%? Doesn't that mean you're taller than exactly 50%, but also shorter than the other 50%? 50 on the left, 50 on the right, 50-50? That would make you exactly average, wouldn't it? Uh-huh. All right, you guys ready for cats? It's cat time. Number 6. Let's get a z-score on this small cat. He's this many centimeters tall. Average cat is this number right here. There's my average. Group that together, right? But how small is this small cat? Huh? I have to divide by the standard deviation. Tell me how small in context. This is my small cat. Ooh, he's a little small cat. And this z-score, again, a unitless value. Okay. Is that a multiple choice answer? 1 point. Yeah, it's right there. It might round a little bit. You have to round it a little bit. Just like that. Right. Now, yeah, for completion, I'm going to bridge tomorrow. What is negative 1.27 as a z-score? Negative 1.27, right there. 0.10. Guys, 0.10, is that like 10%? Is that what 0.10 is? 10%? Okay. So my cat with this z-score is taller than only 10% of cats, and he's shorter than 90% of other cats. We got 1 cat remaining, and this is the last question for today. Number 9. Z-score for, how about a taller cat? How about this cat right here? Subtract the average cat. Right. Okay, so right away, positive value. He's going to be a taller than average cat. But how much taller than average? So divide by the standard deviation. Get a z-score right here. Yeah, that's a multiple choice answer right there. So I'm good on that front. Right, you guys get a multiple choice answer on your 2 cats down here? Good. Okay. And then to bridge over to tomorrow. What are we doing tomorrow? So I got a z-score of 0.63. Okay, so that's on the positive side of the table. It's over here. Greater than average side. 0.6, 60, 61, 62, 63. This says, I'm going to round this to 74%. Okay, 74%. This particular cat is taller than 74% of other cats, which means he's shorter than the other 26%. You guys see that too? All right. And that is as far as I've been getting today. Does anybody have any questions so far? So I'm going to close down this recording and then walk around class and make sure that you guys are all good to go.